Hello everyone, welcome back to another video for the series. I'm Q, and today I brought a very fun and interesting problem from KMO. And I think one thing about KMO is that if you don't know the theorem, you cannot solve it. And I think they really likes making problems related to projective geometry for some reason. Yeah, and this is one of I think was classic example. Um, I think KMS, like Korean Medical Society, I think they proposed two solutions. I'm pretty sure there are more, but um, the two leading solutions were using poles and polars, and the second one was using Pascal's theorem. And the using Pascal's theorem is actually much more simple, and it was much more easier to understand for me, so that's why I want to share the solution. And we're actually going to use 3 tangents lemma 2 here, the one that I proved in my previous video. So let's get started. H is the orthocenter of orchid triangle ABC. Um, ABC. It's more like right triangle. I need to fix it. Shorter. Maybe like this. Yeah, that seems good enough. A, B, C. And let M be the midpoint of BC. So this point right here is M. Suppose AH, the circle with diameter AH meets AB and AC at D and E respectively. So let's show one here. The other one here. To here. Wait. I'm sorry. Let's change them a bit like this. Yeah. And this one can come right here. Yeah, much better. This should be right here. Here. What? 2 dots? No. Why can't I delete it? What? Didn't want to do this, but I have to do it. That looks better. Yeah. I think the midpoint. What? Oh, this is how it looks like. Okay. I think that the midpoint's right here. Somewhere here. Then M can. Yay. We need to draw a circle. That looks perfect. That is H. Meets DM. Oh, D. E. DM. And one more line. One more line. Perfect. Just gotta move that one up a bit like this. And yay. At this point. Oh, wait. A, H, D, E at P. I forgot about that line. From here to here. So this point right here is P, Q, yes. Prove that these 3 points are collinear. Okay. Yeah. Not sure where the drawing went wrong, but I found the problem. This point right here is not like I need to adjust the drawing a bit because no, actually this looks good. No, wait, it's DE. Oh no. A little bigger. Like this. Yeah, this looks good enough. Yeah, so how do I prove that these 3 points are collinear? And usually when we see 3 points and the word collinear, we immediately think of 2 theorems, one Briantian theorem and the other one is Pascal's theorem. But it's very unlikely to use Briantian's theorem here. So let's use Pascal's theorem. Before doing that, let's kind of review what the 3 tangent lemma said, because we're going to use it here. So according to 3 tangent lemma, if you have an acute triangle like this, you draw, no, that's a bad triangle, something like this. You draw it from here to here, that's 90 degrees. Here to here, that's 90 degrees. Um, this is obviously the orthocenter. Um, we know that this circle must be, this quadrilateral is cyclic because 90 plus 90 equals 180. I don't know how to draw it. Oh no, I'll just draw it like this. Yes, this is a circle. And we know that if this is a midpoint, this and this circle is tangent. This and this line and this circle is tangent. And the parallel line that goes like this, that passes through the orthocenter, are tangent to each other. And this is the if and only if condition. So if this is tangent, this is tangent, this is tangent, then we know that this points must be the orthocenter and the foots respectively. Yeah, and the reason why it's an if and only if condition is because when we actually look at the proof, we are only looking at the if and only if steps. So that's why the conclusion is also the if and only if with the initial condition. So we just need to show that dm and the circle with AH as the diameter are perpendicular to each other. Not perpendicular, tangent to each other. And this looks better. Okay, now how do I know it? Okay, so first of all, CD and BE, when we draw them, CD and BE, when we look at the quadrilateral ADHE, they are cyclic because no, not CD, sorry. We're actually going to draw a line like this from here. We don't know if it's D or not yet. Let's call it D prime. Here to here. Let's call it E prime. We know that D prime, H, E prime, and A are cyclic. That is true. And notice that because this is 90 degrees, AH is the diameter. But notice that there is only one circle with AH as the diameter. In other words, D and D prime and E prime are congruent to each other because there exists only one circle. And those two circles that we just found have the same property. Yeah. Sorry. Yeah, then we know that that's why we know that BHE are collinear because E and E prime are E prime. I don't really, I'm quite lazy to write like the form, like the Olympiad style writing. I will just write it like this. We know what E prime is, right? BHE are collinear. Yeah. Then with that in mind, we actually don't have to use the three tangent lemma. We just need to use the fact that this the fact that E and E prime are congruent to each other by using um, the properties. But it's always not bad to prove it. And also, wait, actually, you know what? We need to use it. Yeah, we need to use it because when we define Q, we have to use it. So what is B? B is the intersection of AD and HE. What is P? P is the intersection of AH and DE. Now, when we look at this circle and the quadrilateral, or 4 points ADHE, we know that we could also define Q. And we define Q as DD and HH. Here, D and H are tangent. Are tangent to AH. Like this. Okay, then we're done because we only need to write Pascal. So we want AD, HE to be together, AH, DE to be together, DD, and HH to be together. Yeah. Let's actually change the orders. DE and HH. We write DD because we want to match the number of D and H. So what we just did right here is if we somehow use Pascal's theorem for the 4 and 2 more, so 6 points based on this circle. If DD and H, if point D and H, sorry, if the line tangent to the circle at D and H meet a Q, that we can define Q that way. But how do you know that like this line and this line are actually tangent to the circle? And we actually use the tree tangent lemma there because if DM and HE, not HE, this line is not tangent to this circle right here, then we cannot say that Q is the intersection of DD and HH. But we know that by tree tangent lemma they are, so we could define Q like this and be safe enough to use a Pascal's theorem. So let's continue. How do we do it from here? Yeah, I'm pretty sure I moved it up. Why is it? Oh, it's H. Excuse me. Okay. D, E, H, H. When we do it, we have. Oh. Wait, you're done. You're done actually. Because this one, D, E, H, H, D, D. Just switch the order of these two and these two, so EH. Notice that we have our Pascal. So by Pascal's theorem, with with hexagon ADDEHH, PQB are collinear. Yeah, and that completes our proof. So I think it was somewhat straightforward if we knew if uh, we knew the three tangents lemma, but I didn't know it at first. So I think this problem taught me how to use three tangents lemma, and also helped me review Pascal's theorem. Because when I first tried this problem, I knew that we have to use Pascal's theorem, but I was looking at this line, this line, this line, this line, and this line, this line. So I was like, wait, how am I supposed to use Pascal's theorem here? It's impossible to prove um, that these points are actually on a circle or a conic surface. Yeah, so this problem, I really love solving and learning about this problem. So if we quickly just go over it, what we just did right now is we just proved that BHE are collinear because there exists only one circle that has AH as the diameter. And assuming that DM and I'll say assuming that DM is perpendicular, because we already know that this line right here is tangent to the circle. Assuming that DM is perpendicular, tangent to the circle, we could define all the points like this. And by three tangents lemma, we indeed know that they are tangent. So we could easily define our points like this. And from here, we could use the Pascal's theorem for the 4 points right here. And actually it's 6 because we use D and H twice. And make Pascal and use it and we're done. So I think that's the basic structure of this problem. And it's really interesting, I think. So thank you so much for watching this video, and I'll come back with another very fun and interesting problem tomorrow. Thank you and see you tomorrow. Bye.